All right, I think maybe we can get started. So yeah, let's do that. And this is basically kicking off the last week, so lesson 7. And I think probably won't be the most challenging step in terms of the course because there's not really a lecture for the lesson. This week we covered most of the material that we need for lesson 7 last week, but there's an exercise where you'll have some things to add to the code that we started working with for the last exercise in exercise number 6. And that's perhaps where I will start is with this exercise number 6. Are there any questions or issues that people have encountered?
Maybe with like understanding plots.
Mm-hmm.
So basically these plots showed us 2 geotherms in the time now and in the time like in the past.
Some time ago, yeah.
Okay, so like every time in the past we have linear distribution of this like geotherm. How it's like why?
Yeah, so the question is basically just a question of when you start the model, no matter what time you start at, 50 million years ago, 100 million years ago, the first time it's always a linear geotherm. And that basically comes from the initial conditions for the equation that we're using for calculating the temperature. When we want to solve the problem where we solve the change in temperature with time, so not steady state, but like something where it is dependent on the initial temperature, and the evolution you will see in terms of the temperatures will be a function of how long it has been. In that case, you do have to start with some assumption of what the temperature field was in the past. And this particular approach that we're using, the equation assumes that basically temperature was a linear gradient at whatever the starting time is that you start doing your calculations. So you could do it other ways, but in this case, what we're using is an analytical solution, and the way that it works is basically just to assume a linear gradient at time 0, and then after that calculate how the temperature would have changed. So it's not necessarily based on a kind of geological assumption.
It's just like simplification.
Exactly, yeah.
But like what does the difference show? It's just like a difference in like cooling or heating or?
Yeah, so I mean, basically the difference, the only thing that we're going to see in this equation that's going to be different is you start to see the kind of curvature or bending of the geotherm and the change in the temperature at the bottom of the model. And both of those things are going to be a function of the rate at which material is being moved up, or we don't really explore that, but if we did sort of a simulation of sedimentation, we could do the same equation and just make the velocity negative, so then that would correspond to material being deposited at the surface. But the change that we're seeing is basically just a function of whatever the velocity is for the advection. So you can think about this as like rock being moved up toward the surface and it's being eroded instantaneously so that the surface elevation is never changing. So that kind of flux of rock up toward the surface is causing temperatures to increase. And it doesn't increase in a straight line, in part because of the tendency that the surface, like we assume there's a constant temperature at the surface, and rock has a sort of a limit to how fast it conducts heat or so it transmits thermal energy. So the curvature that you get there is basically a function of this uplift velocity, and over time, it does keep more or less the same shape, but you start to see that there's kind of more curvature the faster the velocity is or the longer the time is. But it's basically just we're allowing the temperature at the bottom of the model to change freely. So it's not fixed there. Otherwise, what you would see is the top and bottom points would stay fixed, and you would only get curvature. In this case, we get curving or bending of the geotherm that's a result of mass being moved up toward the surface, plus an increase in the temperature at the bottom of the model because there's in this equation we're using, there's no constraint at the bottom. We don't assume that the temperature at the bottom of the model has to be fixed. There are other versions of these kind of heat transfer equations where you do assume that the temperature is known or fixed at the bottom of the model, or other boundary conditions you could apply. But in our case, we don't apply a boundary condition at the bottom.
Just to show that what, like that the process continues, or
Well, the idea is basically just to show that as you move, as you erode material and move rock up toward the Earth's surface, it means that you're moving warm rock up, and that tends to increase your geothermal gradient. And it generally has the biggest effect near the surface. And the effect, if you go down 30 kilometers, you will see changes in temperature, but the gradient doesn't change as much as it does near the surface. So when we look at things like this thermochronometer data, where we're sensitive to what's happening 5 kilometers below the Earth's surface, or somewhere, maybe 10 kilometers depth, these are places where this kind of temperature change is important.
like, can we say that the fact that these now graphs plot are upper than previous gradient, that velocity not velocity, how to describe it? I mean, the gradient becomes more, or how to describe this difference?
Yeah, you could say the gradient is steeper or higher. In the case, so after 50 million years of erosion, you have a higher temperature gradient than you had before. And that is essentially just, it's a reflection of having moved rock that was warm at depth up toward the surface. As you move it up, if we didn't have heat conduction at all in terms of the equation we're dealing with, if we moved the warm rock up, nothing would happen. It would just move, from 6 kilometers depth to 5 kilometers without changing temperature. That would be purely just the advection part. But the thing is that we have also heat being conducted, and the temperature at the surface is fixed. So even though you're moving rock up, it is still being forced to cool by this boundary condition at the top. So the gradient can increase some, but in order to have kind of a balance between the conduction and the rate at which material is being moved up, that change in the gradient is basically showing you that. So you put in a faster advection velocity, you'll see the gradient gets steeper, because as the rock is moving up faster, it's harder for it to cool down as efficiently as when it's moving up more slowly. If you set the velocity to be almost zero, you don't really see much change in the temperatures with depth.
And the last question about exhumation history. So we have this plot of exhumation history, which end up in one spot. So does it mean that in this spot exhumation are stopped, and it's equal, becomes equalized with with erosion rate and so on?
No. I mean, basically what it's showing you is we have a model that we run for 50 million years, and since we know the runtime of the model and we know the velocity, you can figure out how deep a rock would be 50 million years ago that came up to the surface today.
So basically this spot is rocks that are now on the surface.
Yeah, and it just shows you the history of what the temperature was if you go back 50 million years. So if you were to include somehow the date or the time at which it was at those temperatures and plotted that, you'd see that it's at time 0, it's at the surface temperature, and 50 million years ago, it's down at the lowest point, which is the kind of starting point for the exhumation as the rock is being moved upward by erosion at the surface.
So basically we can remove this line of today's surface to this spot, and it would be polymer construction, something like that.
Something like that, yeah. Basically, it would just show you each one of the geotherms that you plot shows you the sort of temperature snapshot at that time. So 10 million years ago, what did temperatures look like? That's what the plot would show you. The temperature history will show you basically for this piece of rock that's moving up from depth to the surface, what was its temperature back in time. So it's a little bit different, but it's basically just the history that the rock would record in terms of temperature, which could be used for thermochronometer data, but could also be used in other contexts, like if you're interested in the thermal history for oil and gas purposes. Potentially you could have the same information available there, that this, it's essentially a record of temperature that is contained in the rock, and whether or not you have a system that can record that history. Do you have the minerals that have the the right sort of system to have radioactive decay and a daughter product being trapped, or is there some other thing that can tell you about the thermal history in the rock? That's more of a geological question, but for the plot, it's just showing you what the temperature was back over the 50 million year time that the model has been run, or whatever time you chose, if you run it for longer. Yeah.
Thank you.
Yep. Good questions. Anything else about exercise number 6? All right. If not, we're actually going to go backwards even further to something that was in exercise number 5, and that is, I asked you for course feedback for a point, I think, is problem 0 or something like that in exercise number 5, if I remember correctly. And I do like getting the feedback. It's quite useful, and I also like to make sure that I share with you when I collect feedback, at least during the course, what you guys said. It's nice sometimes to know that everyone else is struggling if you're struggling. So this is a good reason to also share the feedback, and just to see maybe there are some things that people suggested that you felt as well. So just to quickly summarize here, there was, 6, maybe 7 questions. The first one was basically, how are things going in the course? And it was sort of about equally divided between people saying it was going pretty well and people saying that it was quite difficult. So this is not necessarily a surprise. I would say that's about what I expected to see. And I don't necessarily see that as a bad thing. I know the course is challenging, and especially there's a bit of a step up from the GeoPython course. And I hope that by the end, things feel a little bit more clear than they did at the beginning, but I do know it's not necessarily an easy course. And there were some people that also said like it's getting worse. So maybe the first few weeks were not so bad, but then things were getting more challenging. This is coming right after exercise number 4, and I know there were a lot of things that were frustrating about exercise number 4. So I'm also not necessarily surprised about this, and you'll see there's a few things about exercise 4 that come out in the other responses as well. And yeah, I think that's told me some useful things about what to do for exercise 4 in the future. The other thing that came up just in a number of responses was that it's a lot of work. The course is a lot of work, and that you're spending time on it. And well, I guess that's maybe not a bad thing. I don't want it to be something that's so demanding that you can't do your other courses, but I think there's also a lot that you take away from the course potentially in terms of Python skills. So it might be a lot of work, but I have seen in the past people using Python in other courses that they take after this, which I think is a sign that it's worth learning and that it can be quite useful. Yeah.
And also, I had some advert on my phone for a Python course for business, and it was like $200 or something. But I looked at the description out of curiosity. It was like 4 loops, pulling from matplotlib, plotting with pandas, like literally everything we learned in this course.
Yeah.
Like people pay $200 for.
Yeah. No, you can find courses for €1,000 or whatever. Like it's there's a lot of these Python courses that are available where if you were to go out and try to learn these things after being here, of course, it's not like coming to the university is free. I mean, it's free in a sense, but you're not working or something like that for a lot of people. So that means like you're not necessarily bringing in money to cover other expenses like food, place to live, and things like that. But yeah, I mean, I think it's, I don't want the course to become such a burden in terms of the amount of workload that, it starts to be something that you really hate. But I do try to cram a lot of things in here because I think it's stuff that you can use down the line, especially when you get to like writing bachelor's thesis, master's thesis. If you're dealing with data and you want to plot data, you can take a lot of things that you have here and just copy paste them from one of the exercises and start modifying it to make plots for your thesis. And I hope that's the way things will go for at least some of you. So Moving on to the most challenging parts of the course, questions in exercises was probably the #1 response. This again is coming after exercise #4, where I realized the questions were not necessarily in line with what you were doing as clearly as they had been in the year previous. And I've mentioned that before, that we changed the exercise a bit this time, and I spent more time with making sure the code parts were working and less time looking at the questions. So that was obviously something I overlooked a bit there and could be improved in the future. Plotting can be challenging. At least a few people mentioned the plots being a bit challenging, and it is sometimes a bit confusing when you're plotting with pandas. Sometimes you want to plot a data series or a whole data frame, and the syntax is a little bit different, or there can be just some challenges that come up there, and so understand that one. Functions are always something that is a bit of a challenge when you're learning them, and it may not become clear even by the end of this course, but hopefully at some stage, if you continue using Python, you'll start to see the value of functions and being able to just take a single piece of code and reuse it easily in the form of a function. It's a great way to save yourself possible mistakes with like copying and pasting and editing the same chunk of code 15 times in a Python code. So understandable. Again, the exercise 4 questions came up specifically, and there was a few mentions of people having challenges with converting the equations to code. And I know that if you're not so recently having taken a math course or never really got to the stage that you were doing a little bit more advanced high school math, that some of these things are perhaps a bit unfamiliar in terms of the syntax and the sort of what the equations are showing. So then converting it to code becomes a bit of a challenge, as well as the fact that sometimes it's just a mental block. You look at an equation and it just like doesn't compute. So and that happens to even people that are quite experienced. Myself, I have the same thing if I look at an equation, particularly if it comes from a different scientific field where it's the same equation that I know, but they use different letters and things like that. I sort of see it and think I don't know what the equation is doing. And yeah, sometimes you just have to sort of stop and go kind of piece by piece and start taking it apart. So these are all kind of not surprising challenges. Most valuable parts, plotting, I think was probably the most popular response there, so that's good. I hope you'll continue to use the stuff we're learning with pandas to do the plotting. Exercise sessions were also mentioned as being very useful, and I will specifically mention Lotta because her name came up in a number of the responses, so nice work. People are very happy with Lotta's assistance, so yeah, I'm very happy to see that she's getting acknowledged for that, and I wanted to make a point of saying something there. The exercise sessions, yeah, I think it's quite clear that doing these exercises on your own would be challenging. Maybe you can get through some parts of them, but like when you get stuck, it's really nice to have the exercise sessions, and I think that's also a kind of key part of the course. And even for the time, I don't go to the exercise sessions for so much of the time, but I also enjoy being there as a teacher because it is the kind of best time to engage one-on-one and actually kind of help you learn things in Python. So I think they're kind of very useful both for you guys as students, but also for the teachers. I think it's a great opportunity for us to practice explaining things in Python. And there was at least one person who mentioned for loops and functions, so I put that on here because I'm happy to see that people like and value learning about for loops and functions. These are things that if you continue with writing your programs, you'll be using for loops and functions pretty much without question. So that's great that you're finding that useful. For the difficulty, about as expected, average was about 7.3 out of 10. So that's on the difficult side of the spectrum, and I'd say that's about what I expected to see. Minimum was 4, so there's nobody who thinks it's really, really easy. There were no 1 out of 10s. So for me, I think that's not a bad thing, but there were some 10 out of 10s in the difficulty, so you have my sympathies if you're in the 10 out of the 10 part of the responses there. The course is challenging and it's a lot of work, so I'm not surprised to see that. Most people are putting in something like 8 to 10 hours of work per week, and There are some who are putting in more, some who are putting in less, but that is about right for this course level, strictly speaking, on the basis of the hours you should work for the number of credit points. It's probably a bit heavier than most 5 credit point courses, but it's not totally out of the range of what you should be putting in terms of the work time. But yeah, it's a heavy course, and I think this is probably about what you need to do to get through the exercises and things like that. As far as suggested changes go, the few people mentioned this idea that the exercise session could be later in the week. I can try to do that in the future. Obviously, that won't benefit you, but it will benefit the next round of people who come through the course. And I agree that like having the lecture on Monday and then turning around on Tuesday to work on the exercise is not ideal, because perhaps you'd like to get started on your own first before coming to the exercise session. And we have some control on the schedule, but it is using some sort of system now where I can't specify so easily like the day that I want and for the exercise session. So I think actually, I don't recall, last year it might have been that we had class on Wednesday and then the exercise session on Friday, or was it on Thursday? Okay, so exercise. So there was at least one extra day last year. This is the first time I think we've had it where it's been like immediately the day after, so that's a bit unfortunate. So I can see what I can do about that, but I don't know how much control I have, unfortunately. Otherwise, just to point out a couple things here, teaching in the GeoPython style is something people would like. Yeah, I think that would be kind of nice. Certain parts of the course work well to try to do that. Others, like when there's the lectures on introducing some new topic, it's not as easy to do in the sort of GeoPython style, but I could try to do some more of this kind of hands-on stuff where you guys are following along in the Jupyter Notebook as I'm lecturing, for example. More assistance would be helpful. Yeah, I think if possible, we've managed to get an extra assistant this year, but even still, it could be useful. I know the exercise sessions are quite busy. There was also a suggestion that maybe there could be 2 exercise sessions per week. And if we could do that, of course, we would perhaps need another assistant just to operate those, but having 2 sessions a week would be nice. I agree about that one. And then some suggestion about having better questions in the exercises. I think we've already covered that one. Otherwise, most people feel like it's already a master's level course, so the changes that were needed when moving to the master's level the next time it's taught would be pretty minimal. I think I probably will still change a few things, but they won't be kind of major changes that I would foresee. So it's good to see that I think it is about that level, and that's part of the reason why I want to move it up to the master's level. Believe it or not, I have been making the course a little bit easier over the past 3 years, but still I think it's a bit more demanding than a bachelor's level course should be. And then lastly, there was a suggestion that perhaps if it's at the master's level, students could bring their own kind of data or their own problems for some part of the course and work on something where they're kind of doing their own analysis of maybe their preliminary data from their master's thesis or something like that, which I think that would be cool. That would be a nice thing to be able to do, and it depends mostly on the number of students. If there's 30 students in the course, it gets a bit heavy for me to try and understand what everybody's data set is for and to read through all the notebooks and understand everything. But if it's a smaller number of students, that's actually a pretty good option, because I think it would be really useful to get some hands-on help getting started with doing your own data analysis. So, yeah, thanks again for the feedback. I know it's, perhaps you did receive 1 point for giving the feedback, so you had some incentive to give it, but I do appreciate taking the time to give some useful comments, and there's still some things that I probably can pull out of the 34 responses that I received for the course feedback. All right, so that's the feedback summary. Now we can jump here quickly to lesson number 7. The course page is not yet updated, but there's not really anything here that you need necessarily for lesson 7. I'll update this in a little bit. Once the GitHub Classroom link is live, I can update the course page. But essentially, it's the same material that was here for lesson 6 in terms of like the lecture slides and things like that. It's all the same stuff there. Of course, there would be a link to exercise number 7 instead of exercise number 6. But otherwise, that's sort of that. And last year, I didn't record this lesson. I did record it this year, or I am recording it this year, so that if there's anything that comes up in the preview of the exercise or whatever, you can go back and look at that stuff. Before we go to exercise 7, I know there's a bit of concern about this final paper, so I want to maybe say a couple things about that, and then we can go to exercise 7, and then I will stop and you guys can get started. But yeah, the final paper, the tentative due date's still 21st of this month. We can perhaps discuss that after the introduction to lesson 7 is over, if there's people feeling like there's no way that's going to happen. I don't have any strong feelings about extending the deadline a bit. If you want to feel like it's still the 21st of December to see if you can get it done before Christmas, then you don't have to think about this over Christmas break, and that's a good thing. But I do know, yeah, sometimes things don't kind of align nicely, and this is usually a bit tight to squeeze in getting the paper done before Christmas. But yeah, now that you've done parts of exercise number 6, perhaps it makes a bit of sense to revisit this description or kind of overview of what the paper is about. Because I think when I mentioned it earlier in the course, maybe things were kind of too unclear at that stage in terms of what you were going to be doing. But basically, it's meant to be sort of scientific article or scientific journal article style paper, where you take your results from exercise 6 and 7 and put them in the context of some regional geology from the Himalaya. So we've been looking at doing this thermochronometer age prediction stuff in exercise number 6. So you did the calculation of these temperatures, and then you predicted these ages. What you're going to do in this week's lesson in exercise 7 is to take some data for thermochronometer ages that have been measured in the Bhutan Himalaya, and we're going to compare your predictions from the model to the age data in the exercise. Again, you'll be producing some plots, and combined with exercise number 6, some of those plots can then go into this final paper to kind of put together an overview of what we've done in exercises number 6 and 7, but in the style of a scientific journal article. So what that means is, like, there's these different sections in here. These should look somewhat familiar. The abstract is going to just be a kind of brief summary of the paper. The introduction is not necessarily an introduction to exercises number 6 and 7, but you can think about it more like an introduction to the scientific question or sort of interest in this study area. And if you read through, there's a few papers that I suggest as reading for putting together this paper. You'll see in there that basically what we're looking at is questions about the rates of tectonic movement, so how active are different faults, versus erosion, and what role does climate play. So if it's like changes in the amount of rainfall, that's something that could influence how fast the landscape is eroding. So this introduction section is basically meant to kind of give you, or give the reader, me, some idea of what the kind of broad question is. And you can look at some of these articles that are referenced there to see what are they presenting in their introduction, what kind of question are they asking, and certainly you could be writing things in the same style. So you should state the problem that you're addressing in the first paragraph, and then after that give a little bit of background, like maybe referencing the lecture notes or referencing some of the other articles about what has been done, and then maybe a short paragraph about what you're doing. So this could be something like, there's questions in the Himalaya about rates of tectonic and erosion processes over millions of years, and then you kind of give some information from some of the articles about that, and then, you know, in the last paragraph you just say, what I'm going to do in the paper is to use a numerical model to compare predictions of thermochronometer ages to data from the Bhutan Himalaya to understand better what the rates of these tectonic or erosional processes are from that data. So it's something like that, just kind of setting the stage of what you're going to do. Geological background, again, you can look at a couple of the articles to see, like, you know, we're looking at age data that's going to cover a few million years, so you should maybe talk about fault systems that have been active, maybe something about the patterns of rainfall and climate, and in all of the articles there, there's some useful information about this stuff. The kind of question here is, like, you know, the uplift in the Himalaya is driven part by tectonic uplift and partially by erosion, and what are the things that affect that? And so you can see here the types of topics you should include in the geological background. The methods section is mostly about the equations that we're using and the kind of approach that we're using to predict these thermochronometer ages. So that's the kind of method you're using here, is this numerical modeling. And so you should say something maybe about the equation that's being solved, what you calculate, and some of the other things from here. It's just a description of what you've done in the exercises in essence. So kind of general description of the parts of the functions and the code that you're using. Then in the results section, you can put in a few of the figures that you've produced. So just showing an example of what the code does. So plotting the geotherm, for example, plotting the thermal history, and showing maybe a plot with the predicted and observed age data. So that's what you'll produce in exercise number 7. But these are things you can pretty much take straight out of the exercise and put into this section of the code. And if you're thinking about it and do this in some reasonable way, there's probably 2, 3, maybe even 4 figures you put in here, and you'll start to see the length of the text that you have to generate getting shorter and shorter, because you don't want to put every figure from the exercise in there, but you'll see that when you put in a few figures, you're ending up with maybe less space to fill than you would think. Key thing for the results section is you're just showing what the code does. Don't say anything about necessarily what the results mean, just here's some examples of what the code produces. And then in the section after that, the discussion, that's where you can kind of return to some of these general questions about, well, there's a list of them here, but essentially, what's the meaning of the plots that you've produced? What do you see in terms of changes maybe in the exhumation rate? And this will come from exercise number 7. You'll see that there's differences in the exhumation rates that fit the different age data. So you can say some things about that, and maybe how well the model predictions compare to the observed age data, some of the limitations of the modeling. So if you want to talk about, like, we're only dealing with a one-dimensional world in terms of the heat transfer problem, but nature's 3-dimensional, so there's things like that could be mentioned there. And basically, this is a sort of what's the meaning of my results section, and this could be a few paragraphs before you write brief conclusions. So all told, it should be something like 6 to 8 pages, and that includes the text and figures. References, if need be, can be on like going into an extra page or something like that. And if there's an appendix, like if you put in your code from exercise 7, your Python function there, you could paste that at the end in an appendix if you like. Are there any questions at this point? I mean, I know we've gone over this once before, so I just thought that since now you've done exercise 6, it might be useful just to have a reminder of what this is, and maybe makes more sense now that you have some idea of what's going. Yeah.
You said that we have to like bring our graphs in as part of exercise 7, showing how to create a picture file.
So we can do that. I think we covered it actually back in the GeoPython lesson 7, and GeoPython covers how to save a plot to a file. But So we can certainly add a hint about how to do that on the course page, or like you can ask us how to do that. It's quite straightforward. The other thing, though, is that there is, maybe here, I'll just open this. There is a template for the final paper available from the course page that is a Jupyter Notebook. So if you want, and I would actually encourage you to try this out if you feel like you are up for it, you can basically write your final report in a Jupyter Notebook. Instead of using Word or something like that, you can just write it in here, which means that you can then, if you want to produce a plot, just call the age predict function at a given place in your Jupyter Notebook to produce the plot, and then it shows up and it's directly available inside the notebook without having to save it as a separate file. This is nice in a sense because basically, yeah, your appendix means you can just copy and paste the different functions you need down at the end of the code. You run those, and then you can, wherever you have a cell where you want to produce a plot, you just run the function to produce that plot in that location. And I think it's nice because this is essentially using a Jupyter Notebook for what it's meant to do, combining this nicely formatted text with the ability to have Python code inside the notebook. The only challenge here that I'll say is it's a bit difficult to figure out how long it should be in a Jupyter Notebook. So the suggestion is to, instead of like number of pages, 2,000 to 2,500 words is roughly 6 to 8 pages equivalent. But this is not taking into account figures. So it could be less than this. So if you go through and like just select the text for these different sections and add it all together, it may be less than 2,000 words. And that's not necessarily a problem. But yeah, more or less, the same section headings that are here in the other on the course page, they're all here with their descriptions. So it's something you could consider if you want to write the final paper in this Jupyter Notebook. That's, might be a nice thing to do.
But how we submit this, like the Jupyter Notebooks? We just like push it to.
Yeah, it's the same as, I need to actually update the link because I see a few people have already created it with the old GitHub Classroom link. But basically it's like you get an assignment from GitHub Classroom and it'll be this notebook for the final report. So then you just save your changes, commit to Git, and then it's there on GitHub.
And should we say like to someone that we decide to use Jupyter Notebook, so you will see?
We'll see it if you use the Jupyter Notebook, but if you, for instance, create the notebook and then decide to send a file separately, I think,
it's better to inform.
If you do something like that, like if you create the Jupyter Notebook for this final paper and then decide to send it separately, just maybe, I don't know, send a message and email to make sure that we know not to think you didn't do the final paper or something like that. But actually for the submission of the final reports, I also need to think about, I think last year people emailed them to me, and that can be a little bit difficult to keep track. So I may make another option for submitting the final paper if you're writing it in something other than Jupyter Notebooks. Well, actually what you could do is you could still create the GitHub Classroom assignment and just put a Word document there on GitHub instead of the... So if you wanted to drag and drop a Word document there, that would be one way to deal with it. Well, so yeah, the question is, how would you do that? Basically, if you go to the repository on GitHub, there's an option to upload files there. So if you've made your own version of one of the exercises, I haven't done this for exercise 7, but like I have my exercise 1. So this is like my copy of exercise number 1 from the course. So what you could do is you could just hit the upload files button and then select your Word document that has has everything there, and just upload it that way. And you can kind of name it whatever, because we can go and see what's in each person's repository. It's not, we won't be kind of auto-grading these final reports, so we've got to go to each repository and download the files anyway. So I can mention how to do that. I don't, like, there's a limit of 100 megabyte file size for GitHub, but I can't imagine anybody's going to get to 100 megabytes with a Word document. So that shouldn't be a big concern. Okay, one last thing before the preview of exercise 7 is I did also want to note on the course page that you can find here the description of like how many points each section of the paper is worth, and what each section should do to receive full points. For instance, for the introduction section, it should clearly state the problem you're addressing, present the requisite background, and state how the exercise contributes to that problem. So if you do that, then you should be getting close to 20 points for that section. For the results section, just as another example, you should describe, clearly describe the results from your experiments and include only relevant figures. So like if you just dump all the figures in there, and most of the time I'm not going to give you full points for that, because it doesn't seem to me like you actually thought about which figures are important and which ones are maybe not as important in terms of the understanding which results are most useful. So anyway, you can look through here if you'd like. I'm generally not really strict about the length limits unless you've gone way over or way under. But you can see basically here what you should put into each section if you want to get full points for each of them. This is just linked from the final project page. Yeah. Any questions about this final paper? Again, I know we've gone through this once before, so it's maybe not so pressing. All right. Then let's go here, just a quick preview of exercise number 7. It's going to look a little bit familiar because it's a follow-up on exercise number 6. But we've got 2 problems. And first one's kind of setting up your code. And the second one is using the code to compare your predictions from this numerical model to some age data. Again, we're working in the Bhutan Himalaya, and I'm just going to go through a little bit of what we have in here. So part 1 is basically redoing exercise number 6. Well, it's not redoing exercise number 6 in its entirety, of course, but basically getting the code back to the same state that it was in at the end of exercise number 6. So this is going and copying what you had done in exercise number 6 for like the modifications you made to this age predict function, copying those and pasting them into the cell here. The cell here. So you should basically go and take what you had in exercise 6 toward the end. I think it tells you specifically after which problem. Copy that and then paste it in here so that the code does everything it did at the end of exercise 6 as the start for this exercise number 7. Because exercise 6 is still being worked on until tomorrow, I can't really put the solutions from exercise 6 in here and not expect you to kind of take advantage of that. So that's why I think they're done this little bit clumsy way. Part 2 is going to be reading in a data file. So we've got this data file here, and it's got some latitude, longitude, elevation, and then different age data that have been measured in the Bhutan Himalaya. So these are all sample locations, and in some cases there are, for instance here, there's an apatite, uranium, thorium, helium age, and then it has its standard error along with it. Don't worry about handling the standard error and standard deviation differently in the misfit function that you'll use in here later. That's not something we want to mess with. But basically, I just put in here that these are different. There's standard error in one case and standard deviation in the other. A bit frustrating, but that's what it is. But you'll see in here there's some minus 9999 values as well. So for some of these sample locations, there has not been, like for instance here, there has been no apatite, uranium, thorium, helium age calculated. So there's a minus 9999 there to indicate that it's basically missing the apatite, uranium, thorium, helium age. But there is a zircon helium age in this case, and then there's no muscovite argon age for that sample location. So when you read the data file in, you're going to have to deal with these minus 9999 values and convert them to Na values in, or not a number values in pandas. We've done that before. It's been a little while, so you may need to go back even to the GeoPython lessons to see how to convert a certain value into not a number. But otherwise, when you read the data file, there's not a whole lot you need to do in terms of specifying only certain columns or things like that. You can just read it in, but you do have to convert these minus 9999 to not a number. The other thing you have to do here is you have to create separate data series for each of the different thermochronometers. So we have apatite, uranium, thorium, helium. We have zircon, uranium, thorium, helium, and we have muscovite, argon, argon. So same age as we were predicting last week. We have now data for all three of those. And my suggestion is to make some pandas data series. So you're just taking a single column there, maybe one called AHE data. And it should be the column of the data frame without the not a number values. So we want to remove those. There's a reason for doing that will become more clear later in this part of the exercise. But basically, we want to make a separate series for each of the data types with the not a number values removed from it. And so that's the other thing you have to do here when you read the data file in. After that, it's on to calculating a goodness of fit. This equation should hopefully look familiar. It's something we saw back in exercise 2, and then we've seen versions of this chi-squared equation in several exercises since then. But we're using the version from exercise 2, be aware. And here, what we're going to do is create the function first. You can, if you're smart about it, go and take a look at what you did in exercise 2 and do some copying and pasting. After you've done that, we're going to then set the code up in a way such that the age predict function can calculate what the misfit is, or the goodness of fit, for the different thermochronometer systems. So you should have these variables called AHE misfit, ZHE misfit, MAR misfit, and each one of those variables would be like the misfit between the predicted apatite, uranium, thorium, helium age and the ages that are in the data file. One thing that's different from our earlier versions of using this chi-squared equation is now our expected age, or this value here, the kind of prediction we only have one predicted age. Our model only produces one predicted age. So you need to make sure that your function works in such a way that it takes a number of observed ages, but compares them always to a single predicted age. It's not that difficult to do in terms of modifying what you had before, but just something to be aware of, because there's not a corresponding expected age for each observed age, but there's just the one. So you'll do that, and then you'll be able to calculate what the misfit is for each of the thermochronometer systems, and you should also return those values at the end of this age predict function. So you should add to the return statement these three values in this order. The reason that we made these data series, in case you're wondering, is that basically now when we want to go and use this chi-squared function, we don't want to have the NA values in there. And I think we probably could include them and work around it, but it's just easier to create a separate series and then drop the NA values out, so we don't have to worry about those being in this chi-squared misfit equation. So that's the second, or I don't know, I guess third thing, but second kind of main task. After that, it's on to visualizing the data. So here, I've already found a typo. We're going to basically produce a set of subplots. So last week we had just this geotherm plot with the thermal history and things like that. We're going to add a second panel underneath it, where you can plot the observed ages and then your predicted age. And there's some description here about how to do that. But the lower plot's basically going to be showing, as a function of latitude, what the ages are for the different thermochronometer systems, as well as your predicted age. We'll come back to that maybe in the hints for this week's exercise if you get confused about that. But yeah, you're basically then modifying the plotting there, and at that point you're done with any code changes, and then it's on to problem number 2. And the goal in problem number 2 is to fit the observed thermochronometer data with our numerical model. And the way that this works is we have these misfit values, and you want to find what rate of excitation gives you the smallest misfit. And we do this first for the combined misfit, so that's the misfit for all 3 thermochronometer systems. You say what rate of uplift or what excitation rate is the, we'll give ages that are best overall fit to all of the age data. And once you've done that, you then go through and go system by system and say, okay, well, if I only worry about these apatite, uranium, thorium, helium ages, what rate fits those the best? And you'll see the rates are a little bit different between the different systems. They're not dramatically so, but they are a bit different between the different thermochronometers. And so you'll have a different rate for each one that gives the best fit to the age data. Once you've done that, you're done. And so I'm hoping this won't take you a tremendous amount of time, although the plotting is going to take a little bit of time. It's a bit more, well, we have to use the matplotlib style of doing subplots, so it's something we haven't done very much of. So that'll be a little bit of something that might take a bit of time, but we'll be here to help and answer questions and things like that. So hopefully we can make this as painless as possible. Are there any questions about exercise number 7? All right. If not, I'm going to fix the one typo I noticed here, and if Lotta happened to see any other things, I will fix those quickly, and then I'll post the GitHub Classroom link on Slack in the next few minutes. Yeah.
I have a question. Which plot we include to the final report? Because do we decide what to include, or there is some obligatory plot that you have to include?
I wouldn't say there's necessarily any obligatory plots to include. I think you'll see that a number of the plots from exercise 7 are things you're going to want to include. So when you have these plots where you're seeing the observed ages and then your prediction, there's going to be at least a couple of those that you want to include, because really that's where you're comparing to the age data. And so that's the sort of most meaningful thing. But oftentimes we suggest that students include maybe 1 or 2 of the plots from exercise 6 before that, so you can kind of illustrate how the code works. Even sometimes in the methods section, it can be nice to have a plot just showing here's an example of the geotherm calculation, because as you guys maybe feel, the code combines a number of different pieces, and it's a little bit complicated. We have our temperature calculation, we have the thermal history that's being recorded, we have the age prediction, and now we have age data. So if you just sort of jump right to showing those plots, of course, I would understand what you're doing, but it's good practice to make sure that maybe you show an example in the results section, in the methods section of just what the plot looks like when you calculate the ages by themselves, the temperatures by themselves, just as an illustration of what the code is doing. So, yeah.
Thank you.
Yeah. Anything else? All right, then I will, like I said, make these last couple changes and get you a link in Slack here for exercise 7 as soon as possible.